Sir, you are live. You can interact with the learners.
माझ्याच्यात दिसत नाहीये पण
येईल सर. आता जस्ट काही सेकंड मध्ये लोड होईल. म्यूट करून सर व्हिडिओ क्वालिटी पूर्ण बिलो 144 पिक्सेल. आता जस्ट काही सेकंड मध्ये लोड होईल.
Hey, good evening, students. Welcome to this second live interaction session for this chemical process control course. Initially, we'll go through the questions which were posed in the Excel form which was sent to you, Google form which was sent to you, and then I'll address the queries which are posted in this chat. So the first question is from Ragul R. Actually, he has sent a lot of questions. So let me go through them one by one. The first question is how to develop transfer function matrix for system with single input and multiple output. So in such a case, I don't know what exactly you mean by transfer function matrix, because in that case, it will not be it will be a matrix with just one row and multiple columns. It will not be a square matrix, and the procedure will be very similar. At one time, you give a step change, or you try to identify the model between input and each output. So you will get multiple such transfer functions, and then you will put them in a matrix. So if you are online, then and if this answers your question, that's okay. If you have any other doubt, you can post it into the chat window. The next question is how to find degree of freedom for a given process. So for any process or any general equation system, degree of freedom, there is a definite formula. What you see is degree of freedom is number of variables minus number of equations. So if you have more number of variables than equations, you will have positive degrees of freedom. The simplest example I can give you is the equation is, let's say, x plus y equal to 10. So here you have two variables, x and y, and there is only one equation, that x plus y equal to 10. The degrees of freedom will be 1. So you can specify either x or y, and then automatically the other variable will get fixed. So that's how you find degrees of freedom for any system. For a control system, we follow the same process. We write the dynamic equations, and depending on how many dynamic equations you have and how many variables we have in that system, the difference between those two will give you the degrees of freedom. I think in the video I have already explained it for a single or simple tank system where there are two variables, F, the input flow and the output flow, and variable is, the equation is volume, dV by dt is equal to F in minus F out. So in that case, you have one equation, two variables, so the degree of freedom is 1. That is why we can control the volume using one controller. So you have put in some question here. If I get time, then I will go through this. You have said that help me solving this problem, you should actually post this into the discussion forum, and then my TAs can answer this. The next question is, we know that system for which crossover frequency doesn't exist is always stable. Suppose if I have a system whose phase lags are minus 60 and minus 190, are these systems stable? So phase lag is a function of frequency. I don't know, when you say phase lags are minus 60 and minus 190, are they at a certain point? So I'm assuming that you are saying these are the end values. Like for a first order system, the maximum phase lag you can have is minus 90. So when you say your phase lag in a system can go up to minus 190, obviously at some point of time it will also go to minus 180. And if at that case the amplitude ratio is greater than 1, then the system can become unstable. I have a doubt in this part. In most of gate problems, the frequency is given in radian per second. If I put this radian per second directly into any trigonometric function without converting into degrees, whether I get the answer in degree or radian. So it's all about which. If you are using calculator, you have to specify whether the calculator has to take angles in radian, degrees, and I think that should solve the problem. Difference between turn down ratio and rangeability. So I don't know what you mean by turn down ratio, but rangeability is what is the range. So when I completely when I open the wall, how much at what percentage of wall opening the flow starts to come, because typically for even small opening there will not be any flow, and similarly towards the end after 95% or so the wall will saturate. Even if you increase the wall opening, the flow will not change. So typically rangeability would indicate that range of the wall opening over which you get variation in the flow. So I hope Ragul, your questions were answered. Next question is it possible to crack GRATE exam by preparing only last year question paper? Again, this is outside the scope of this course, so I would not comment on it. Most of the problems in the assignments are MATLAB based problems. Can you please provide access to free online MATLAB? So I don't think so. The problems which I have put into assignments, they are all solvable by hand. I had used MATLAB to demonstrate things because then it's easy to visualize. But I don't think your assignment problems require MATLAB. That is why I have not opted for that MATLAB service which NPTEL or Swayam courses allow. So if you have any specific question which you could not solve by hand but required MATLAB, you can post it into a discussion forum and we'll look into it. So those were all the offline questions. So let me now see if there are any questions in the chat window. Somehow I'm not able to see any questions in the chat.
Sir, are you able to see the chat?
It says chat disconnected. Please wait while we try to connect you.
Sir, can you refresh that page again?
Okay, I'll try to do that. Okay, now I see the chat. Yeah, so the only questions I see are by Tushar Gujarati. Please provide more practice problems for transfer functions with detailed solutions. I don't know what you mean by this. Transfer function with detailed solution means what? What do you want to do with the transfer function? Can you elaborate more on that? And also, is there any free software like MATLAB or some Excel template? So for NPTEL courses, MATLAB is available, but for this particular course, I had not opted for it because none of our assignments or exam problems are gonna need MATLAB per se. As I said earlier, the MATLAB I had used MATLAB to show the responses. If you want a free version, I think Scilab also you can use, and it has similar functionalities like MATLAB, and you can do all these calculations, transfer function solutions in Scilab also. I'm not sure about Excel being able to do this directly. I'll be back in a minute. Many questions are with transfer functions based to practice such questions, more practice problems. Yeah, but I'm not getting what. So all the questions are going to be based on transfer function, right? Most of the questions. So in which area you want? So right from our dynamics, we use transfer function. For controller design, we use transfer function. So everywhere we are going to use transfer function. And just changing numbers, you can get the solution. I don't know what you mean by uh, more practice problems. So are there any more questions about the parts which covered, even the parts which we covered before the live session one? Yeah, you can email, and then I can respond. I'll get more clarity about what exactly you are looking for. So in general, I'll just go over the overview of the course till some more questions come in. So we started the course by understanding dynamics. Even though the course is on control, in order to control something, if you want to tame something, controlling a chemical process means we are just taming our chemical plant, because it has its own ways of operational and we want the plant to operate the way we desire. So in order to control anything, even if you have a pet and you want to train it, what you need to understand is its dynamics. How does it behave? If I do this, is it good for the plant, or how does it react? So all those things are needed before we really develop a strategy of how do we train us something. So that's exactly what we did in the first 1/3 of the course. We try to understand how a plant or how a process behaves, and we took a more general approach of dynamics. So we looked at different classes of systems. We looked at simple systems like first order systems, second order systems, and then we clubbed everything which is higher than that, because those even if you look at a third order system or a fifth order system, in general they are going to look responses are going to look very similar. So we try to understand the simple type of dynamics like first order, second order systems. Then we looked at numerator dynamics, which gives rise to interesting things like inverse response, or it gives you overshoot without oscillations. And then we concluded that with the notion of poles and zeros. Now that is a very general notion, not necessarily limiting only to chemical processes. Everywhere, electrical engineering, mechanical engineering, wherever you talk about dynamic systems, people will talk in terms of zeros and poles, and that gives you a general summarizing perspective of dynamic system. The moment you know zeros and poles of a system, then you can predict how the system is going to respond. So after those 3 weeks of dynamics, then we moved on to the control. How do we use this information of dynamics in order to develop control? And we looked at only focused on one commonly used strategy, that is known as a feedback control strategy. I believe in the introductory lecture, I might have even told you about other strategies like feed forward strategy, combined feedback, feed forward. So those are used, but very commonly used strategy or the bare minimum control which any process has is a feedback system. So we spent a lot of time on formulating what is feedback strategy, how do you derive the overall relationship, like the overall transfer function for a feedback control system. What are the simple control actions like P, the proportional action, integral action, derivative action, which forms the core of a commonly used controller known as a PID controller. We saw individually what P does, what I does, and what D does. And then we moved on to the aspect of stability. So stability means if we want a system to behave in a sense like rationally. If I want to give an analogy with a real like human beings, so if somebody is behaving rationally, we'll call him stable. If somebody is behaving irrationally, in the sense that whatever we do, the response is not unexpected, or response is outside our scope, we call it as an unstable system. So we looked at the stability, and it is important from both points. One is if the system is unstable and you want to operate it at that point, then you definitely need a controller. Otherwise, the system will not be practical. You will not be able to operate it practically. A very common example of that is a exothermic CSTR. You might have studied it in CRE. That there are 3 steady states, and typically we are interested in the middle steady state, which is unstable. So in order to operate the reactor at that unstable steady state, a control system is required. Without that, the reactor will never operate at that point. And the other way around is a system may be stable, but if you put a controller and it is badly tuned controller, badly selected controller, the stable system can become unstable, which is worse, because then your job as a control engineer is to make sure the system behaves better in the presence of control, and you have actually made a stable system unstable. So from both points of view, it is important to understand the stability of a system without control, we call it as an open loop system, and also a possibility of a closed loop system. That means when you put a controller, is the system going to remain stable or become stable, or can it become unstable? And then that puts some bounds on what sort of values for controller parameters you can choose. So we use the stability analysis in both Laplace domain and frequency domain to check whether the system remains stable or unstable. And then that gives you some bounds about what is the maximum value of controller gain you can use, for example. And then we moved on in week 6 to controller design, the feedback control design, which has 3 aspects. One is we have so far looked at only one input, one output. So if you have multiple inputs and multiple outputs, how do you pair them? Or how many controllers would you use, whether it will be a single input, single output controller, or multiple input, multiple output controller. So that is the synthesis part. The second part is selection. So once we know that this input has to be paired with the other output, what kind of controller will it be? It will be a P controller, PI controller, or a PID controller. So that is a selection problem. And then lastly, if you have selected the controller type also, then what are the best values of P, Kc, tau I, and tau D? So that forms the tuning problem. And then we looked within tuning problem, we looked at the standard methods like Ziegler-Nichols tuning or Cohen-Kuhn method. Some are open loop tuning methods, some are closed loop tuning methods. So if you actually end up operating a plant, then you will realize that lot of the control loops in the plant are not very well tuned. So one simple thing which you can do to improve performance of a plant is to tune those controllers. So this information will become very useful for you if you are operating a plant. You will see that there are some control loops which are always oscillating. They are never at steady state. They were never very close to the set point. So in such cases, it will be very useful for you to try to tune those controllers. And I believe I have also shared some inputs about some heuristics about how do you go about tuning a controller. There are some standard methods. There are some heuristics. There some the plant which the system, the DCS system which you are using may also have a feature like tune the controller, auto tuner. So you can use any of those and try to tune those controllers, or you can manually tune a controller by simply saying that if you have a lot of oscillations, you may try to reduce the integral action or reduce the gain, and then that will help you in terms of reducing those oscillations. Automatically the controller performance will be better. Then in week 7 we started to move towards so all week 4 to 6 were about feedback control, and then in week 7 and 8 we try to look at the extensions of these, like up to week 6 we looked at only single input single output control. But what if you have more inputs and less outputs? It is very less likely. Or the other way around, we have more outputs to control and less inputs. How do you go about controlling those? If you have secondary disturbances, how do you speed up the response? So we looked at the traditional advancements like cascade control, split range control, selective control, override control, ratio control, inferential control. And then the later half of that we looked at the more model based controllers like IMC, internal model control. What if we know the transfer function of the process? Your PID controller doesn't require transfer function to design the controller, but if I have that information, can I make use of that information and develop a better controller? So those are model based controllers. The more practical extreme of that would be the MPC, the model predictive control, which is not similar to a PID controller, but it is more like an optimization based controller. And if you see more like sophisticated plants these days, you will see that you will have PID controllers at a regulatory level, and you would also have an MPC which will try to optimize the operation of that particular plant. And then in last week we looked at again two more important aspects. One is about multivariable control. So rather going from single input, single output to if you have multiple inputs and multiple outputs in your process, which is typically a case, because your plant will not have a single input and single output. You will always have many inputs and many outputs, and lot of times if I change one input, it will affect lot of other outputs. So in such a case, how do you go about designing a controller? Can I still use single input, single output controllers? In that case, you have to check whether those controllers are going to be interacting or not, or I have to use a multivariable control. Typically, the way our plants are configured is we still go with single input, single output controllers, and we try to use some sort of a model based controller like MPC to coordinate the action of all these controllers. So that's why I said some of the high end, typically good, well instrumented plants would have PID controllers at the base level and MPC to sort of allow multivariable control. And then lastly, we looked very briefly talked about batch process control. Because all this discussion we had, everything we said that something has to be at set point, and then either some disturbance tries to affect the process or we want to change the set point. But if you talk about batch, there is nothing like steady state. The batch is always dynamic. So the control challenges, there are a lot of additional challenges which come in when you have a batch process. So we spend some time in terms of batch process control, especially in terms of you have sequences. You have to multiple steps to be carried out in a particular sequence. So how do you ensure that those sequences are followed? There are sometimes some constraints that unless something happens, you should not do this or you should not do this. So those are called as interlocks. So how do you incorporate those? So we talk a little bit about ladder logic. So typically in a real industrial sense, these ladder logic and all those chemical engineer typically would not involve into those. Instrumentation engineer will be the one who would be dealing with setting up this ladder logic for a control system. But it's, especially if you have some problem in the process, the instrumentation engineer would not know what is the physical reasoning behind the system not working. So in that case, you will have to collaborate with him to find out this problem. So it will always be useful for you if you have some basic or working knowledge of ladder logic. So that is why I had included that portion as well. So that's in a nutshell what I had covered in these 8 weeks. The idea was to cover some basics and also give you some flavor of what's out in there in the industry and what are sorts of extensions. If you talk about the current state of the art, these by no means is the thing which you will see in industry, because as I said, many or most of the industries you will visit, especially if they are good enough, like medium to high scale industries, they would always have some sort of an MPC controller there. And if you talk about research in this area, obviously what I have talked about is like 30-40 years, like not exactly 30-40 years, but at least 20 years back. So a lot of research has happened, though some of it has been practical, some of it has not been practical, has not been implemented practically. So there are a lot of things which go after this. So this is sort of an introductory course to process control, I would say. So with that, let me see if there are any more questions. Course videos are very good and interesting. Thank you. So thank you. Welcome. Please explain positive and negative gain. Can you elaborate more on this? What do you mean by positive and negative gain of controller or process? Pushpendra, are you online? Can you write more about this? controller. Okay. So controller, if you say, let me just share something that will make it easier. Okay. Okay, let us take this very simple controller like a P controller. So now, when you say controller gain being positive or negative, so I'm talking about this KC to be positive or negative. So how do you decide whether KC has to be positive or negative? And that has its implications. So it depends on the process gain or the overall process gain. See, if you have to look at it from the point that what should the controller do when the error is positive or when the error is negative. So let us say you have a system. Let me see if I have a system here. So this system, which was a surge tank, liquid surge tank, and I want this level to move from 50 to 50. Yeah, so it was, I think, the response to a disturbance. So the feed flow rate had increased. So what's going to happen as the feed flow rate increased, the level increased. So your y set is 50 and y is going to be, let's say, 51. So your error is going to be negative. So now when your error is negative, what you want your input to do? Your input is the outlet flow rate, which is currently at 50. So as your height has increased, you want your output flow rate to increase. So here the equation I have shown is in terms of deviation. So the real u, this is the deviation in u. So this is u minus u steady state. So my height has increased, my error is negative. But in order to bring my level to constant, what I need to do is, as my input flow rate had increased, my outlet flow rate should also increase. So I want this deviation to be positive. I want u minus us to be positive because I want my outlet flow rate also to go to 51. So that my inlet flow rate will be equal to outlet flow rate and the level will stabilize. So my error is negative, but I want this deviation to be positive. In order for this to work, my KC has to be negative. So this is the case here where your controller gain will be negative. So this type of controller, we call it as a direct acting controller. So direct acting controller is such that if the output goes above the set point, my input, the controller action should also increase. So that is known as a direct acting controller. These are the cases where gain has to be negative. The other type of system, even though I don't have an example here, some cases you would want that when this error is positive, your deviation should also be positive. In such cases, the controller gain will be positive. So it depends on what is the relationship between input and output. And this gain of the sign of KC depends on what is the process gain, what is the measurement gain, and what is the wall gain. So the product of all of them has to be positive. So that is, you can take it as a rule of thumb. Typically, what you would see in any stability criteria is KP, KC, KV. That product has to be greater than or has to be positive. So if your process gain is negative, your controller gain most of the cases will also be negative. I am assuming that KV and KM are equal to 1. So in that case, if process gain is positive, KC will be positive. Process gain is negative, controller gain will also be negative. But that is very limiting case when KM and KV are also 1. if they are not one, or they can also change, because a lot of times you have walls which have negative gain, like you have fail open wall. So if you fail open wall, the kv will be negative. In that case, even if kp is positive, your kc has to be negative. So you have to look at it from the simple perspective, which I think I have discussed in videos also: direct acting controller or a reverse acting controller. So direct acting controller is a controller such that if my output goes above the set point, my control action should increase. So increase in output above set point corresponds to increase in the controller output. That is a direct acting controller. For that, controller gain will be negative. Controller gain will be negative. And exactly opposite is true for a reverse acting controller. So if you follow that, irrespective of whether wall has a positive gain or negative gain, everything will get taken care of. So that's that's what we do with positive or negative gain. So I hope that was sufficient for you. Okay. Do we have any other questions?
If there any no question, we should wind up.
Yeah, so I don't think there are any more questions. So I hope you enjoyed the course, and send me any. Wolfram Alpha is it good for online solutions? Is there any Excel template developed for offline use? I'm not aware of anything in Excel used for control. So who enjoyed the course, do send me feedback in terms of the videos or anything about the course, so that it can be improved for any future offerings. And if you are taking the exam, then all the best, and stay safe. So I think with this, we'll try to close out this second live session. Thank you, and have a good rest of the day.
Thank you, sir.